Hello, everyone. Hope you're doing well. We're going to close out our videos this week by summarizing a few of the major theorems. Now, this is our last video for this week, and I'm going to make it a little bit of a shorter one since we had a longer one talking about Cauchy and completeness. So let me mention a few things that are going to be important about this video. One thing that's going to happen is I will explain the proofs that are going to happen here. I purposefully went through and selected proofs that I thought were not only intuitive, but also different from the ones that are given in our textbook to show that different perspectives can get us to the same places sometimes. Some of these theorems and proofs will look more intuitive to you than those in the text. Some of them will look less intuitive than the ones that are in the text. My encouragement to you is to try and work through both. Some will use sets, some will use sequences. There's going to be different ways of approaching each of these theorems depending on how you go through it, and find the way to go through these theorems that is the most comfortable for you. One, that's going to tell you this is the way that I want to go through and prove some of the problems that I start seeing in these homeworks. Two, you know your weak spots. You know the things that you want to work on a little bit more, how to become a little bit more comfortable with some of these topics. So my encouragement to you is to really start digging deeper into the proofs that we've been going through and doing this. Do this also with the proofs that we have already discussed. Find those proofs and say, oh, these were the good parts that I felt really good about. And then find the parts that I was like, oh, I'm not really feeling this part, or I need to go back and go through this again. And that's totally okay. You may notice this from my talks, and I say this as in complete transparency. Maybe it's because I see it more than other people might, but I see my own weak spots when it comes to understanding and being able to explain different proofs. Writing proofs is something that has come natural to me at this point, but when it comes to explaining proofs, sometimes I do well in some parts than better in some parts than I do in others. So take time and see if you can fill in from some of my weak spots, the places in which I do not have the same strength as maybe you could have in going through and making sense of what's going on in a particular point or in a proof. So take time to read through the proofs again that we have already discussed and start looking through them very carefully. As we begin moving into metric spaces, we're going to see that there are parts of these spaces that are familiar and others that are unfamiliar. I am purposefully using language and choosing types of proofs here that are going to be very easy to translate into the language of metric spaces going on. Now, there's going to be some of the proofs here that are not going to translate very neatly into metric spaces at all, and we're going to talk a little bit about why they might. We've already seen one reason why some things may not be as easy to translate from the real numbers into this general metric space is that I've hinted that metric spaces don't have a notion of a total ordering, meaning that I can't just pick any two numbers and say one is less than, greater than, or equal to them. We're going to see how that makes a big deal in some of these other problems that we're looking at, because we're going to see a lot of less than or equal to signs, a lot of greater than or equal to signs. Now, some of these are going to be okay because we're going to be taking y values. And so you could think, okay, instead of taking functions from the reals to the reals, if I'm taking functions from a metric space to the real number, although I can't say my x values have less than or equal to, right? I can say my y values have less than or equal to. So I'll kind of try and highlight some of these points as we get through the proof so that you can see what parts might translate neatly from metric spaces and which ones do not. But regardless, when we go through and see these proofs, we're going to need a clear understanding of the definitions that we're working with, as well as a strong hold on the proof framing with each of these types of proofs that we're going through. These theorems are going to be a touchstone for us in another way, which is that we're going to see if we can show these sorts of things from metric spaces in some way or another. Having something called an extreme value theorem is going to be interesting for us. In what ways can we say we have an extreme value theorem in a metric space when we don't have a closed interval to be looking at? Because we can't say our x values are in between a and b, because that would be a less than or equal to relationship. So what are the ways in which we can have an extreme value theorem? What are some of the ways we can generalize the results that we're used to in analysis on the real line to uh, these metric spaces, which are much more general and useful because these things that we're mapping things from don't have to be just numbers. They could be functions now, which is very useful in the study of Fourier analysis, which is a kind of a historical impetus behind much of the material that we've been developing. But knowing how these things come about in terms of what we're using in the proofs and how our definitions and stuff are put together. That's going to be a big part of today. So let's see if we can find those connections here using these theorems. Some of these proofs I'm just going to say, and I'm going to leave some of the connections of them to you. These are all complete proofs. No proof ideas here, but trying to understand what's going on with here within the proofs is going to be very important. Our first theorem that we're going to be talking about is the intermediate value theorem. I've given a formulation of it that you might get the most general formulation for it in some other place. Let's start with a function going from a to b to the real numbers. Let's assume that this function is continuous and that f of a and f of b have opposite sign. That is, f of a is positive, then f of b is negative. Or if f of a is negative, then f of b is positive. Then there is a point c in the inner set, right? We may know these as the interior points of the closed interval from a to b, such that f of c is equal to 0. So the most general notion of this theorem is one that says, let's say that f of a and f of b are all are bounds of a value of d, right? Some value of the inside. And you're looking for an inner point c so that f of c is equal to this y value of d. But you can start translating the function up and down to get to any point that you would like for an intermediate value theorem once you have it in this state. So we're going to call this the intermediate value theorem. Lindstrom begins this with a set, and we will actually do a sequential proof of this theorem by attempting to do bisections, very much like in this picture here. As I go through this theorem, use this picture to kind of help us see what we're trying to do and doing a little bit of bisection with this function. Let's start by taking two sequences, A1 and B1, all the way up to there. And we're going to define more elements of these sequences as we go along. But let's let the beginning of these sequences be the left and right endpoints. So these are x values for us. A is A1, B is B1. Then we're going to engage in an algorithm known as bisection. So starting with A1 and B1, if the object in the middle, so let's say, for example, we're looking back in this picture. If the thing directly in the middle of A1 and B1, which would be this value right here, if this is positive, then we're going to say, okay, let's look for a 0 outside of this region. Because here, for example, I got something in which this was this side with this side, so I'm getting something which is maybe positive over on the B1 side, and then maybe negative over on the A1 side. And then I'm going to start bisecting my interval a little bit so that I know that where I'm starting from was negative and where I'm ending from is still positive. Look at that there. Okay. So in this particular case, this is without a loss of generality, and I'll go ahead and make this note here. We're saying that f of a is less than 0 and f of b is greater than 0. Otherwise, we would have to go through and switch which ones we are making a sub n and b sub n in this case. So here, notice now that we have made a bisection and said that if f of a sub n plus b sub n over 2 is greater than or equal to 0, then let us keep the next element of our sequence and the a sub n's the same, and let's make our new b sub n element this bisected spot. The goal behind this is that this should still be a negative element, or rather, f of a sub n plus 1 should still be less than 0, and f of b sub n plus 1 should still be greater than 0. Notice here, if f of a sub n plus b sub n less than over 2 is less than or equal to 0, then I am now going to make this another negative element, but this time closer to the b sub n, which I'm just keeping to be the same thing. By our construction, b sub n plus 1 should still be greater than or equal to 0. But since f of a sub n plus b sub n over 2 is less than or equal to 0, I'm going to make f of a sub n plus 1 and be able to say that this is less than or equal to 0. Now, first you might be asking, John, there is a chance that f of a sub n plus b sub n over 2 is equal to 0, right? So which option should I be taking if f of a sub n plus b sub n over 2 is equal to 0? Well, then I have good news for you. That a sub n plus b sub n over 2 that you just found is exactly the value you're looking for in the intermediate value theorem, because you just found a value where f of that value is equal to 0. So at that point, you can stop. You can terminate the process. No need anymore for any sequences. So after that, you can say, okay, if f is greater than, you know that you're going to be changing your b sub n sequence. If this is less than, you're going to be changing your a sub n sequence. And notice that in each and every one of these steps, your sequence elements are getting closer to each other. Your a sub n's are always less than or equal to 0. Your b sub n's are always greater than or equal to 0. And that's exactly what we say here in this part of our definition. Note that b sub n minus a sub n is getting smaller and smaller. The distance between them is exactly half the distance of the distance between the previous elements in that sequence. Then we can use an epsilon argument to show that these two sequences converge to the same point. We can call that point C. Since f is continuous, we can say that since a sub n approaches the c, f of a sub n being less than or equal to 0 implies f of c is less than or equal to 0. Here we're using that limit definition of convergence, which is that the limit as n approaches infinity of f of a sub n is equal to f of the limit as n goes to infinity of a sub n, in which case that's f of c in this case. So because of that, since each individual element being less than or equal to 0, f of c needs to be less than or equal to 0, and the same thing can happen from the opposite side. If f of b sub n is greater than or equal to 0, then f of c is greater than or equal to 0. Well, since f of c is both less than or equal to 0 and greater than or equal to 0, f of c is equal to 0 as we desired. So this is the intermediate value theorem. Maybe you liked this theorem more than the other one. Notice that this notion of bisection is not quite possible in its current form with metric spaces, as we may not have notions of addition and division. But if we can find a way to, say, given any 2 points inside of our region, bisect it, right, we can maybe start thinking about how you could start tying this into more general spaces. I encourage you to start building in that intuition there with bisection. Maybe there is a way to think about, cutting spaces up into different parts and allowing those parts to shrink. That could give us maybe an intermediate value theorem for some more general space we come up with later. Note that also that the guaranteed point C in the previous proof comes from the fact that the converge, A sub n and B sub n, do not have to be convergent sequences the way we drew them up. They're merely Cauchy sequences. They do not have to converge. Here's an example of why the intermediate value theorem does not hold in the rational numbers. Maybe not something that we thought about. If you take a function from the rational numbers from 0 to 2 to real numbers and define it to be f of x equals x squared minus 2, we know that the 0 of this function would be square root of 2 in the real numbers. Then the sequences that we get out of a sub n and b sub n, I've gone through and calculated, are these sequences. Both sequences get closer to the whole where x equals square root of 2 would be, but since this value is not in the rational numbers, there is no value c where f of c is equal to 0. So a neat little fact that shows the intermediate value theorem does not hold in these non-complete spaces. Completeness is going to be important in what is to come for us in these more arbitrary spaces. Let's take a look at our next theorem. This is to help us this is useful in proving Bolzano-Weierstrass, which you may know is the theorem that says that every bounded sequence has a convergent subsequence. So let's start by proving a little lemma here, something that we had used a little bit before, given some intuition, which is that every sequence x sub n contains a monotonic subsequence. Let me give some intuition on the reasoning behind this lemma before we continue. Let's go back to our notion of limit superior and inferior. Notice that this sequence kind of goes all the way around, so it's kind of tricky to think, how could I find that there's a limit superior or limit inferior here? It's a little tricky until you realize, wait, the circled and the diagonal elements here are actually kind of giving me some help in finding a limit superior versus a limit inferior. This could be thought of as a decreasing subsequence here. Similarly, we could have an increasing subsequence for this if this particular sequence goes on for infinity. There's a few issues with just kind of taking this argument as it is. The reason is, right now, you're looking at a place where the sequence elements that define the limit superior or limit inferior of this sequence actually continue to decrease or continue to increase. It's very possible that after you get to a certain point, that this just stays at this point for the rest of the sequence, right? Maybe you never get to another point. Maybe all of our points are above this particular sequence, kind of like in our -1 to the n plus 1, 1 plus 1 over n example, this one that we had over here. So maybe they don't quite work the same way as we would like them to have, all right? So um, we need to think a little bit more carefully about how we get to these points. So what we're going to do is we're going to do a similar thing to this, and you're going to see that our definition of what we're going to call a turnback point in this proof is very similar to how we are writing these points in the limit superior versus inferior, but we're going to be a bit more careful with how we proceed with our argument. Let's define some x sub k in the sequence x sub n to be a turnback point if no element past x sub k is greater than x sub k. That is, that x sub k is equal to the supremum of all the x sub n where n is greater than or equal to k. You might notice, by the way, that that's exactly that circle point on the graph that I showed you from before. What happens if there are infinitely many turnback points? Well, then you can just take the sequence of those x sub n. That's exactly what our argument is telling us that we can do for that. It's that you can just take those turnback points, x sub nk being the subsequence. That is very much like the circle points that we have from up here on the top line. Those infinitely many points are a subsequence, which is important that we have infinitely many, so that they can become a subsequence. Gives us a decreasing subsequence, which is the monotonic subsequence we are asking for. Well, what if there are finitely many turnback points? Well, then there's going to be a farthest turnback point. There's going to be a point kind of like here in this picture. You can imagine maybe the farthest turnback point is this last one that we see here. And then everything else past that has the property that it is less than or equal to this turnback point. Well, so for example, x sub n plus 1 is not a turnback point. So that means that there's going to be something farther along in the sequence that is going to be greater than it. And I'm going to call that farther along element x sub n sub 1. So x sub n plus 1 being not a turnback point does not have the property that no element past x sub k is greater than x sub k. That allows us to find some element past x sub n plus 1 that is greater than x sub n plus 1. And that's exactly what we have found here in this space. Now, the point x sub n sub 1 is also not a turnback point. So we can do the same thing. There is some n sub 2 greater than n sub 1, so that x sub n sub 2 is greater than x sub n plus 1. You might notice that we can continue this process ad infinitum because there are every element past x sub capital N is not a turnback point. So every point does not have this property, which means we can always find this sort of chain of sequences. So we continue this process to get an increasing subsequence that continues along through here. Notice a few important things in this process, one of which is we need the elements that we are choosing in our subsequence to always be farther along the sequence than the previous one was. So for example, here's a non-example of a subsequence. If I am given a sequence x1, x2, x3, so on and so forth, non-example of a subsequence of this would be something like x sub 10, x sub 100, x sub 50, right? This being lesser along, like this looks like it's farther along in the subsequence, but it is not inside of the same order of the list as the original sequence. It's like I'm jumping around back and forth. That causes a lot of problems for us if we end up trying to make our subsequences like that. It makes it a little bit inconsistent in how our subsequences are proceeding. They don't seem to be proceeding in the exact same way that our sequence is proceeding. Because of this, we're going to end up seeing a lot of like strange little idiosyncrasies, come out. As a result of that, it's going to be harder to define limits based off of things if we don't know, okay, I know that everything past a cutoff point in this original sequence is within epsilon. So how do I know that for this subsequence when the millionth element in this subsequence could be x sub 3? Right? Like that's something that I want to be able to deal with and talk about as it comes along. So we always are going to ask for our subsequences to be in the case where we have something that is x sub 10, x sub 100, x sub 200, or x sub 201, right? Having sequences in this way where whenever you are looking at farther along elements in the subsequence, you're also looking at farther along elements in the sequence. So notice that sort of property. That's the first thing. The second thing is notice that we actually were able to sometimes find a decreasing sequence and sometimes find an increasing subsequence. It's not always the case that you could find both. Sometimes you can only find one or the other. For example, you might think, okay, well, how would I find a decreasing subsequence and an increasing sequence? That's not possible because every subsequence of an increasing sequence would still be increasing. So sometimes we can only find one or the other. If we get to a proof and it says, maybe we can only get to this point and we're like, oh, well, we just found a decreasing subsequence, we can immediately find counterexamples to that and be like, wait, maybe our proof isn't quite what it needs to be. So maybe there's something I need to look into a little bit more or start discussing a little bit. So take a look at this as kind of like a way to be able to find counterexamples. We found a way to construct a decreasing or an increasing subsequence depending on the number of something called turnback points, kind of related back to this notion of the limit superior sequence. Now, from this lemma, that actually does a lot of the heavy lifting for us in the Bolzano-Weierstrass, which here again says that every bounded sequence in the real numbers has a convergent subsequence. Notice that we just said that every bounded sequence has a monotonic subsequence. Well, now we have a subsequence which is monotonic and which is also bounded. A monotonic bounded subsequence is convergent by the monotone convergence theorem. And so we can just reference that theorem and say we're done. We have found our convergent subsequence. A neat little corollary of this is that because we could be saying something bounded in Rm is bounded in each coordinate of R, as well as everything that is going to be there in that sense, you can get for each monotonic subsequence of each component, you can find a convergent subsequence. You can eventually find a convergent subsequence in Rm. I recommend taking a look in the book there for some of the details, but that particular detail comes up a good bit if we are generalizing notions of things that work in the real numbers to things that work in Rm. That's two theorems already. Let's keep it going. Let's talk about the extreme value theorem for a second. Extreme value theorem is sometimes not necessarily called this when we go through this in calculus. The extreme value theorem is this. It says that if you have a continuous function on a closed interval, so if you have something that goes something like this, then you might have what are called local maxima on that interval, maybe something like this and something like this. But this is saying that there exists an absolute maximum and minimum on that interval, that there is a greatest possible value of what that function can be on that interval. So if a comma b is a closed and bounded interval and the function f is a continuous function, then f has this absolute maximum and it also has the absolute minimum. Here is our absolute maximum, whereas we may only be able to call this a relative maximum. And then here is our absolute minimum, whereas we may only be able to call this a relative minimum. Notice that we aren't talking about the notions of relative max and min in this particular theorem. We will do that in kind of build up to another theorem. Instead, we're just talking about the absolute max and min of these functions for this theorem. Let's go through the proof of the existence of an absolute maximum. So notice here, first of all, that we are defining absolute maximum absolute maximum and minimum in the following way. We are saying that the absolute maximum is the point C such that f of x is less than or equal to f of c for all values of x inside of the interval from a to b. So that's our rigorous definition that we're going to try and manipulate a little bit for this absolute maximum. So here's how we're going to do it. Well, first, let's let m be the supremum of all y values of this function. Now, notice that we haven't proven this theorem yet. That might be an obvious statement. But something that's interesting about this theorem is that before I draw this picture, you may not even know that the supremum of these y values is even finite. Because the fact that we're on a closed and bounded interval, it doesn't actually tell us, are we actually going to go off toward infinity at any point here in this function? You might start trying to work around this a little bit by saying, okay, well, if we did, we'd have like some sort of asymptote, or we'd have some sort of discontinuity, some break in the graph. I'm not going to go through each of those case-by-case bases. Instead, I'm going to go ahead and say, okay, let's start by saying that this supremum could be infinite. And I'm actually going to show as a part of this proof that m has to be finite. So let's do it like this. we're going to use the fact that the thing that's closed and bounded is our set of x values. Starting here, m is the supremum of our y values. If there is a value c inside of this closed interval such that f of c is equal to m, great, we are done. That's our goal. We are trying to find this value of c. Otherwise, we have two cases. If m is finite, then for a given epsilon greater than 0, m minus epsilon is not an upper bound because m is the least upper bound by definition of supremum. So there is some value x inside of this closed and bounded interval so that m minus epsilon is less than f of x is less than m. Now here's what we're going to do for this bullet point. We're going to let epsilon start shrinking. If we do that, we're going to find a sequence of x values. Maybe epsilon is 1 at first, and then epsilon is 1/2, and then 1/3 and 1/4. And what we're going to get is a sequence of x values, because for each epsilon we can choose this value of x, that corresponds such that the corresponding f of x values approach this value of, I should have made this capital M. This should be capital M right over here. So the corresponding x values or y values approach m here. So in our picture, what we're doing is we're saying that m minus epsilon for this absolute maximum is going to give us a particular x value. Maybe it's a value over here, such that the y value of that x value is somewhere in that window underneath the absolute maximum. Now notice that for places like this underneath the window, you could be going around to this relative maximum, but eventually you're going to find a cutoff point that cuts off that relative maximum, and you're going to need to start coagulating around a specific point, this other absolute maximum of what you're looking at, in which case you can start seeing that maybe these x of n actually do converge to the absolute maximum. That's the bit of intuition that I can give here for this. So we're making a sequence of these x values so that the corresponding y values approach the value of m. If m is infinite, on the other hand, by the way, this is not going to end up being the case, but because we haven't rolled that out, we have to talk about it. Then we are going to use the definition of a sequence of y values going off toward infinity. Then for a given cutoff point in the y-axis for some n in natural numbers, there's going to exist some x value inside of a comma b so that f of x is greater than n. This allows us to form a sequence of x values such that the corresponding y values approach infinity. So here, for example, you can imagine that the picture is you have your quote-unquote continuous function that's going up this way, and you're continuing to make higher and higher cutoff points. But because the supremum is infinite, this function cannot be bounded. So that means that you're always going to be able to find x value points inside of this closed interval that gets you higher and higher up through the function. Either way, the sequence x of n is a bounded sequence inside of the set a comma b, which means that it has a convergent subsequence by Bolzano-Weierstrass. Let C be the limit of this convergent subsequence. Now here is the rub. Here is what we just used. Bolzano-Weierstrass said, the thing we just proved, that you can take this sequence of x values and find a convergent limit for those values. Now that's going to be our key to this. Notice that x of nk is going to converge to C. Since f is continuous, we're going to use that sequential definition of continuity one more time, which tells us that the limits of the y values of the function are going to approach the y value of f of c. So notice here we're using again that definition, limit k goes to infinity of f of x of nk, this time with the subsequence here, equals f of the limit as k goes to infinity of x of nk. And that is f of c by definition of what we are saying this limit is. On the other hand, f of x of nk, remember, this is the thing that we were saying approaches m, which could be, again, finite or infinite in this case. M, that is the maximum value of this, or the supremum value of this function. Now we get to say a ton of things all at once. One, notice that this is the limit of x of nk equaling m, and that the limit of f of nk is equal to f of c. So we actually say that because limits are unique, f of c is equal to m. Now we get to say a million things. One, f of c is equal to m. This supremum is actually a maximum of the function. That means that we actually are inside of the set a comma b because there exists an x value such that its y value attains the value of m. It's not just a least upper bound or anything like that. We also get to say that m is finite because this function is defined at x equals c. It's not undefined. It's not going toward infinity. It is an actual value. It's a point. So this absolute maximum is finite. And finally, c comma f of c is an absolute maximum for this function on this interval. Notice that I'm not saying that it's the only absolute maximum for the point on this interval. We could have a place in which two points separately reach the absolute maximum, but that's okay. We only wanted to say there was an absolute maximum, and the convergent subsequence helped us find one of those 2 points. You can imagine that maybe you have a bunch of points around each of those points, but we ended up finding a convergent sequence that converged to one of these absolute maxima. So this is the proof for a closed and bounded integral in calculus that we use. This is the same way that we go through and approach that. We have a similar theorem if f is a closed and bounded region in Rm, but we aren't going to go through and prove that here. We can see here that we aren't going to be able to take vectors in Rm and say things about less than, greater than in terms of their x values, but we can say things that are less than and greater than in terms of their y values. So you might be able to notice that with respect to our x values here, we actually never use the fact that our x values were greater than or less than at any particular point. We just said that they were inside of this closed and bounded region. So you can start thinking about how you could generalize this theorem to the world of Rm, instead of it just being on the real line. There's one last theorem that we want to go through and talk about, and that is this theorem called the mean value theorem. Recall that the derivative of a function f, we're going to need this formula for sure, is defined to be the limit as x approaches a of f of x minus f of a divided by x minus a. We say that a function f is differentiable at this point a if the limit on the right exists and it is finite. Here is our picture to help us out with the mean value theorem. Some of you may have seen the mean value theorem before, but maybe you have a picture in your head that's very much like this. The way that the mean value theorem works, and again, this is something that is important to us because it tells us something about kind of like, you can think of this a little bit as like a intermediate value theorem for derivatives, although it's a little bit stronger than that. It says that you can take a secant line between any 2 points and find a slope of a tangent line that is of the same slope as that thing. Let me check something real quick here. There we go. So we're saying that if you take the slope between a and b, then what you get is this. Change in y over change in x would give you the slope of that secant line. Whereas you're saying that there is a point in the interior of that interval that gives you the slope of the tangent line. I'll use a different color for it. The slope of the tangent line. And that's going to be this guy right here. You want the slope of the function going from a to b to be exactly the slope for the point at c, just the tangent line given right there. The mean value theorem says you absolutely can find something like that. That when you are going, and this is another way to think of it, again, this is a little bit weaker than the mean value theorem, but it's the intermediate value theorem for derivatives. It says that when you're looking at the derivatives of a continuous and differentiable function, then what's happening is you're starting from something, a slope given right over here, and it's going to reach all of the possible derivatives as what you end up with over here. The secant line, in some sense, is taking an average of all of those derivatives. You're going to be able to reach a tangent line derivative that hits exactly that average. That's the general notion here for what we're doing with this mean value theorem. It's a pretty incredible result, and it uses some of the things that we've already been talking about. Let's start by proving Rolle's theorem, which uses a lemma of its own, which says that if you have something that is a maximum or a minimum, this one is can just be a relative max or min instead of an absolute max or min here. If you have a function that has a relative max or min at an inner point inside of where it is defined, where the function is differentiable, then we can show that the derivative of the function at that point is equal to 0. The general picture behind this is that you've got a graph here that is reaching a general maximum, like this one over here. Notice here that if I'm looking at this definition of f of x minus f of c over x minus c, slopes of these secant lines over here, that these are going to be positive slopes on the left, coming from the left, while these are going to be negative slopes coming in from the right. But because the slope of the tangent line can be thought of as the limit of slopes of secant lines coming closer and closer to it from either side, since this limit has to exist by the definition of differentiability, it is either greater than or equal to 0. It is both greater than or equal to 0 and less than or equal to 0. Hence, it must be equal to 0. And that's exactly what is this theorem. So let's say that c comma f of c is a maximum. Well, f of c is greater than or equal to f of x, regardless of where you are inside of this interval. If this is a relative maximum, by the way, you would have to shorten this closed interval just a little bit. You'd have to say in a neighborhood around the point C, right? So you could say or in a neighborhood around C. Another way to just kind of cheat your way around this is to say, oh, I'm just going to make the closed interval from A to B small enough so that this is an absolute maximum in that neighborhood. Well, f of x minus f of c is going to be less than or equal to 0 just by moving some stuff around here. And we can notice what happens when x is less than c or when x is greater than c. If x is less than c, then I can divide these two values, f of x minus f of c and x minus c, and get something that's non-negative. That value right there is exactly the one that we're going to be taking a limit of as we go through. As we can see now that the limit as x approaches c from the left for this particular value is greater than or equal to 0. On the other hand, if x is greater than c, then this value is going to be less than or equal to 0 since x minus c is greater than 0. So the limit as x approaches c from the right for this function is going to be less than or equal to 0. Our notion of from the left and from the right, by the way, is exactly the notion given here. If I take values that are of x that are less than c in doing this limit, then this slope that I get is positive. This value that I get here is greater than or equal to 0. Whereas if I take values of x that are greater than c, like points over here, then what I'm getting from my slope is non-positive. I'm getting something from that opposite side. So thinking of left and right-handed limits here in terms of this picture is really helpful. The only values I'm plugging in for x, instead of them being directly to just directly in a delta neighborhood of x, I'm saying that they could be anywhere to the right or anywhere to the left. Hopefully, as we get closer and closer to the value of c, those y values approach somewhere. And indeed, in this case, that's exactly the case because we know that this limit exists. Whenever a limit exists, left and right-handed sided limits must be the same. Since the left-handed limit is greater than or equal to 0 and the right-handed limit is less than or equal to 0, they must both equal 0. There's no other choice. Hence, the limit of this, which is the f prime of c, is equal to 0. And that gives us this lemma that says, essentially, all relative max and min have to have a derivative of 0 at those points. Rolle's theorem says that if you take a continuous function that is differentiable on its interior, if f of a equals f of b, then there's going to be a point c going from a to b where f prime of c is equal to 0. Notice that this is saying, okay, well, if we can show that there's a maximum or a minimum on this, then we've already got the point that we're looking for. So let's see if we can do it. Since f of a is equal to f of b, either the function is constant, in which case the theorem certainly holds, as any point here is going to have a derivative of 0, or the maximum and minimum are inner points. Okay? So that means they are inner points. So for example, if you attain your maximum at f of a, well then f of b has nowhere else to go. It's f of a is equal to f of b. So you cannot go up, right? So that's essentially what this is sort of saying. So the maximum and minimum of this function are going to be inner points. By the previous lemma, these points have derivatives equal to 0. That is, namely, the maximum and the minimum that you have defined. We know by the extreme value theorem, these exist by the extreme value theorem, that you actually get these maximum and minimum. So because of the fact that we proved that theorem first, we can just use that as part of our proofs for Rolle's theorem. That is, because you have a function going from a to b, if f of a is equal to f of b, you have a place in which there's a maximum or a minimum, and it has to be inside because f of a is equal to f of b. So these points have to have derivative equal to 0, and that's exactly what we're looking for. So the picture here is a little bit different than that of what we saw from the original for the mean value theorem. You just have 2 points on a function that are exactly the same as one another. So think of this as like this is the mean value theorem where that slope of the secant line is equal to 0. Well, then you are absolutely going to be able to find a point somewhere inside of there, namely a maximum or a minimum inside of that point, in which you have a kind of a tangent line. That's a tangent line. That's the same thing as what's given right there. Okay. So this gives us a lemma for Rolle's theorem. And the last thing that we want to do is try and work with functions that are not with a secant line of 0. So something like this. Well, the way that we're going to work through this is we're going to take a different function. Let's say that this is our function f of x. And we're wanting to say, okay, we want to get to a slope of a tangent line that equals the slope of the secant line. Well, then something that we can do is we can take our Herculean strength and we can start taking this function and break it down a little bit. Maybe we can subtract by the function by the secant line. So for example, let's say that this function right here is f of x. And let's say that this secant line over here is something like g of x equals whatever the slope of the secant line is, in fact, f of x minus, or f of b minus f of a over b minus a times x, perhaps with a little translation in there if needed. But if I take the function h of x to be f of x minus g of x, then I'm going to get a picture that looks very much like this. It's going to be very much like my Rolle's theorem picture, in which everything has been moved down one to the x-axis, but two, the beginning and ending points of my function are now at the same point. F of a is now equal to f of b. You can even plug that into this function and see that that's actually what you end up getting, is that namely that given what we have, you can notice that h of b is going to equal h of a, given this definition of f and g. And that's exactly what we're going to do. Notice that that's what's happening here. The only difference is we may not be starting over at 0, so I'm going to take this and make this f of x minus the function f of b minus f of a over b minus a times x minus a. So this is to say that this is going to help us out with plugging into parts of this function. So we just do this x minus a to say this is going to be moving this x minus a down a little bit. This corresponds to subtracting the function by a translation of the secant line connecting a comma f of a and b comma f of b. Now you can notice that we actually get something where g of b is equal to g of a in how this is written. Both are equal to f of a. Hence, there's going to be a point c where g prime of c is equal to 0. Finally, we just need to go back to our original function f and say, okay, can we now say that there's a point where the slope of the tangent line is equal to the slope of the secant line? Well, note that the derivative of this function that we've gone through and defined is f prime of x minus this slope of the secant line that we were working with. So if g prime of c is equal to 0, we have 0 equals f prime of c equals f minus f of b minus f of a over b minus a. And adding that slope of the secant line over, we get exactly what we were looking for, namely that the slope of this tangent line is the slope of the secant line. And that's exactly what we wanted. So Rolle's theorem is kind of like the specific case that we end up breaking things back down into to get to the more general case. You'll see us do this a lot as well. Having something that is a very strong, solid, good intuition type of base case to be working with is amazing in some cases. So knowing that these things work in Rn are great because sometimes you can just boil down things in metric spaces to how things look in terms of Rn. We'll do this sort of type of proof writing process as we go throughout this particular course. Let's do one quick problem before we leave, just kind of connecting some of these ideas to see how we can use these problems to solve other types of problems. Let's do this one. Suppose that you have a function from the reals to the reals that is twice differentiable. Show that if f has 3 zeros, that means that there exist 3 values. We can say they're x values, x1, x2, x3, where the y values corresponding to each of those x values is equal to 0. Then there is a point c in the real numbers where f double prime of c is equal to 0. Maybe you have some ideas on this one already, especially given what we've just gone through. If f has three zeros, well, one, I notice that f of x1 is equal to f of x2. Notice here, again, I'm assuming that these are three distinct zeros, so x1 is not equal to x of 2 is not equal to x of 3. Let's go ahead and without loss of generality say that, in fact, f of x of 1, or x of 1 is less than x of 2 is less than x of 3. So this is without loss of generality. Otherwise, I could go through and reorder. So f of x of 1 is equal to f of x of 2. That is the setup for a problem that I'm familiar with. This is a problem in which I am looking at Rolle's theorem. Remember, Rolle's theorem asks for me to be continuous on the interval as well as differentiable on the interior of that interval. Well, our intervals here are the real numbers. And in fact, we're differentiable everywhere. Remember, we're using a fact, which is that differentiability implies continuity in order to do this. Any function that is continuous or differentiable on an interval is also continuous on that interval. So we don't need to state the continuity part. We can just say by Rolle's theorem, we have that there exists a value, and maybe we can call this one C1, inside of the interval going from x1 to x2, such that f of C1, or rather the derivative of C1 is equal to 0. Similarly, because f of x2 is equal to f of x3, then we can use Rolle's theorem one more time to say that there exists a C2, this existing inside of x2 to x3, such that f prime of C2 is equal to 0. Now, you might be wondering why I'm doing this. I notice here that this seems to have a similar conclusion to Rolle's theorem, but that the difference is that it has it's a twice derivative rather than a first. So why am I trying to use Rolle's theorem, which tells me things about f prime, in order to get to f double prime? Well, from my intuition, the thing I'm trying to do is just say, oh, I see that this is similar to Rolle's theorem. So I'm going to start playing around with Rolle's theorem and see if eventually I just stumbled into this idea. Right now, I've got some information about the first derivative, and I would like some information about the second derivative. Well, I'm going to make a quick note here about what I've just discovered. Note, f prime is continuous and differentiable on R. And that's by that's because f, the function, the original function, is said to be twice differentiable. Because of this, I can actually see if I can apply Rolle's theorem to the function f prime. So Rolle's is we're going to apply Rolle's theorem to the function f prime. So here, for example, I notice that f prime, that's not going to let me do that, f prime of C1 is equal to f prime of C2. And that's because, well, first, both equal 0. Well, that's going to imply that there exists a value of C inside of the interval going from C1 to C2. Notice, by the way, that this is the correct order of the interval because C1 is inside of x1, x2, C2 is inside x2, x3, and we have these inequalities here, such that f prime prime of C is equal to 0. But that's exactly f double prime of C. So f double prime of this value of C is equal to 0, and that's exactly what we desired. So if f has three zeros, then essentially we get to use Rolle's theorem twice on the function f to get to f prime, and then f prime gives us 2 points that we can then use to find the f double prime point in the middle there. But that will do it for us today. We've been talking about a lot of exciting theorems here, talking about the intermediate value theorem, Bolzano-Weierstrass extreme value theorem, and the mean value theorem today, and talked about how each of these things might differ if we're trying to take their approaches in more general spaces, as we're going to attempt to do starting next week. A very exciting week for us. As well as different ways of approaching them using different perspectives. Maybe you have now perspectives that you like. Maybe there are parts of this proof that you were like, oh, I need to look at those things one more time. If you're good with all of this, great. That means you're coming in with that solid foundation into these next weeks. We're going to start new material starting in week 3. We are done with our review, although we'll toss in little bits of review here and there as we see fit. But the main idea is that at the end of the day, These are some of the touchstone theorems that we're going to be looking to see if we can prove in other spaces. Do metric spaces have an intermediate value theorem of some sort? Do they have an extreme value theorem? Some of this stuff is very important to us as we start seeing that our metric spaces have very important applications to some of our later applications in the second half of this class. But that'll do it for me today. Thank you so much. Have a wonderful day.